Hey everybody, welcome back. This is another episode of 145 Bootcamp, and today I want to talk a little bit about regression analysis theoretically. We've looked at in other videos how to run a regression in Stata, looking at data in Excel. This is the theoretical part, and so what we want to think about here is how do we design a hypothesis, how do we design a regression, what the constraints are and what the goals are. And so what we're going to talk about here is, first of all, what a hypothesis, a testable hypothesis is, and then how we construct a regression designed to test that hypothesis. So the first thing we want to think about is what we're trying to answer. And with the regression analysis and with the research hypothesis, we're trying to answer the question of what drives a single variable. And when we're thinking about that single variable, we're talking about the dependent variable, the variable that's dependent on everything else in our regression equation. So I'm going to go ahead and write it up here. The dependent variable is going to be the y, the thing we want to explain. We want to explain wages or educational attainment or GDP growth, something like that. This is the variable of interest. I'm going to go ahead and write dependent variable underneath it, and that's what it is. It's dependent because it depends on the model we choose. Okay, so that's our dependent variable y, our variable of interest, the thing we're trying to explain. And then the other half of the equation is going to be how we explain changes in y. And that's what you want to think about your hypothesis being. You want to pick some variable, x, that has a causal effect on y, causes y to change. So I want to say years of education change wages, or investment dollars change GDP growth, or distance from a grocery store changes the cost of living, or quantity of shopping malls changes local GDP. Something like that. But what we have, and that's what the regression is telling us, is that there's a causal relationship. Not casual, causal. That is written totally perfectly. So we have a causal relationship between x and y. And so what we do then is we use slope-intercept form to say, okay, there's some constant alpha, and there's x, and then there's some coefficient beta that helps us understand the magnitude of the effect of x on y. So let me draw it out here for you. So alpha is our constant, beta is our coefficient, and x is our explanatory variable, our independent variable. It's going to explain the effect of x on y. Independent variable. And so what our statistical software does is it estimates our beta, our coefficient, to try and explain how a change in x affects y. And that's basic regression analysis, right? We're just trying to explain how the independent variable determines changes in the dependent variable. And this is where we get to what I wanted to talk about today. So we understand this about regressions. So what are some common biases in regression analysis? And the idea of biases is just this idea that we're not going to do a perfect equation. We cannot perfectly predict a person's wages based on anything. There are reasons why this is true. For one thing, it's hard, right? It's hard to get the data. You'll find that as you do your research, finding the data that you want to answer the question you want to answer can be really challenging. So the data might not be available. There are also things that are really hard to measure. Effort, historically, culture. Those are things that are really difficult to measure. If you think about trying to measure differences in GDP or differences in the effect of a policy change from one country to another, the culture of that country is going to have an effect on how that policy alters GDP. If you think about education or years of experience, those are not they're big determinants of wages, but they're not the only determinants. There are things like effort and chance that play a role that we don't have a good way of measuring. And so our regression equation is always going to be limited by things like our biases and measurement problems. So for now, what we want to talk about are the two most common biases that you see in a regression analysis situation. So the first one is what's called omitted variable bias. And you can see omitted variable bias here in this equation. It's the easiest one to commit because it means you're leaving something out. Omitted variable. There's a variable that's been omitted or left out. So if I'm trying to explain the effect of education on wages, I'm leaving out things like experience, ability, where a person was educated, right? Did they get, maybe they have 12 years of education, usually measure education in years of attainment, but did they get a high school diploma or a GED? Does that matter? Maybe we want to measure their years of education, but we don't have a way to control for how well they did, right? There's a difference between somebody who graduated with C's and somebody who graduated with A's. Maybe there's a locational effect, right? A four-year degree means something different in California than it does in Oklahoma, or it means something different in Canada than it does in Bolivia. So omitted variable bias is just this idea that when we're creating our regression equation, when we're trying to explain our y, we're going to leave x's out, and that's a variable that's omitted. And so it means that there is some explanatory power that's not being utilized. And so the way I like to think of it is, think of your regression equation as being like a machine, right? This equation is the machine that explains y. So if we kind of put it in that context, it's like this big black box. We know that everything in this box explains wages, for example. And I can stick x's in here, and the more x's I stick in, maybe I'll get more explanatory power. But if I don't put enough x's in, if I miss out important x's, then the regression equation, the explainer machine, the wages explaining machine, is going to try and assign that value somewhere else. So, for example, if I include just whether or not somebody graduates from college, that might contain some additional information about effort that person might be committing to education or intelligence. Not necessarily, but if I don't have a measure for things like effort and intelligence, then some of the explanatory power of effort and intelligence is going to be baked into that X of educational attainment. And so when we leave variables out, there's still that variation that has to be explained somewhere, and it's going to fall into our other X's. And we can think about this both ways, because the other really common variable bias that we have to watch out for is, instead of omitted variable bias, on the other end, we could have what's known as a multicollinearity problem, which is when we have too many variables trying to explain the same thing. So let's go back to what I was saying before, right? We're still talking about the idea of what determines a person's wages. We have our equation with an alpha, our constant, and now we're going to have beta 1 x1 plus beta 2 x2 plus beta 3 x3. And so that means that now I have 3 independent variables. Let me show you. I have wages being determined by, let's say, education, years of experience, and age. Cool? Those are all things that could affect your wages. The older you get, the more wages you're going to earn. The more years of experience you have, the more wages you're going to earn. The higher your level of education, we're going to, again, expect a positive relationship on wages. What's the problem here with using education, experience, and age to determine wages? Well, the first problem we have here is now, instead of worrying about omitted variables, leaving something out, we might have too much in. And it's not that we're using too many variables. There's no hard and fast rule about how many variables is the right number. But things like age and experience are going to go together, right? I can't get another year of experience without getting another year of age. And if I stay in the same industry, every additional year of age, I'm going to get another additional year of experience. And so those two variables are going to be really similar. What they might be is collinear. They might have the same pathway, the same relationship with y. And that multicollinearity, multiple variables with the same linear relationship with y, is going to cause a problem for my regression. In this case, I'm kind of over-explaining what happens to y. Age and experience are so similar, they're trying to say the same thing, and that's going to muck up my regression. And so that's another common regression problem is multicollinearity. And we can think about these as not being, again, no hard and fast rule. There's no perfect number of explanatory variables. But you can think about them being two opposite sides of the spectrum. Omitted variable bias, where you don't put enough in and you're leaving important stuff out. And then multicollinearity, when you put too much in and you're repeating yourself, explaining the same thing multiple ways. Both of them are problems. You want to be in the middle where you're using a lot of different explanatory variables to try and explain the dependent variable that you want. Is this a simple process? Heck no, it's complicated, right? This is a hard thing to do. There is an art to this science. That's part of why we have students read a lot of literature and spend a lot of time studying economic models before they do a research project like this, is because we want to give you the tools to help identify which are the useful variables, which are available variables, and which variables are too similar to be included together. Hopefully that makes sense. Let me know what questions you have about multicollinearity and omitted variable bias, and I'll see you next time.